Video, we're going to take a look at the kinematics equations, how we derive them, and how we could use them to solve problems. And we're going to do this by looking at velocity versus time graphs. So we're starting with a pretty generic velocity versus time graph. This object is starting with some positive velocity, and the velocity is changing as time goes on, and the acceleration of this object is constant because the slope of this line is constant. So what we're going to look at to get our first kinematics equation is we're going to take a look at using y equals mx plus b. From this graph, it being linear, it should follow the form y equals mx plus b. And we're going to take a look at each one of these terms and see what they mean on this graph. The y term is a value on the y-axis for any time t. So what's on here is velocity. So I'm going to write v for velocity here, because everything on the y-axis is a value for velocity. M represents the slope of this graph, and we've seen before that if we take rise over run for this graph, that the rise is a change in velocity, the run is a change in time, and the ratio of change in velocity to change in time is something that we call acceleration. So the slope of this graph is the acceleration of this object, so I'm going to put acceleration in for slope. The x-axis is a time t, because time is on the x-axis, plus b. B represents the y-intercept of this graph. So it represents a specific velocity, not just any velocity at time t, but the velocity at time 0. And we call that initial velocity. Because we call this initial velocity, sometimes you see this written as v naught, v with a little 0. We call this v final. And just like with x final in a previous kinematics equation, the final doesn't necessarily mean the last velocity ever. It literally means the velocity where you're studying the object, the velocity at time t that you're interested in. So that's how we get a kinematics equation that tells us the velocity at any time t. And that's this one up here. The next kinematics equation, I'm also going to develop from the velocity versus time graph. But instead of looking at the line, or the slope of the line, or the equation of the line, I'm going to take a look at the area under this graph, because this equation is going to develop the change in position of an object that's accelerating uniformly. Remember, if I take a look at the area under a graph, I get the displacement. Actually, specifically, if I look at the area under a velocity versus time graph, I get the displacement delta x. Not every graph's area tells me a displacement, but this graph's area does. So I'm looking at this, and I could shade in this whole area here. I suppose I could kind of use a color. I'm looking at this kind of strange shape. It's all of this stuff. So when we say area under a graph, we're talking about everything between the function and the x-axis. So I won't go too much farther with this, I guess. You see it's kind of a trapezoid shape. And the easiest way to take a look at this is to break it into two shapes. I'm going to break it into a triangle and a rectangle by drawing a line horizontally across here. So then I'll have this rectangular shape to study, and then this triangular shape. And I'm going to find them separately and add them together. First, let's take a look at this rectangle. The rectangle, its area is length times width. And the length of the rectangle from here to here is technically a change in time. But seeing as our initial time here is 0, and this out here would be some time t, I'm going to say that this length is a time t. The width of the rectangle goes from a velocity of 0 up to the initial velocity vi. So while this is technically a change in velocity from here to here, it's really just vi, since we're dealing with v0 over here. So time times initial velocity. This is the area of just the rectangle. If I look at that triangle, remember the area of a triangle is 1/2 base times height. So it's going to be 1/2. The base, again, the base of the triangle is the same as this length for the rectangle. So I'm just going to call that t. The height from here to here, this is some value v final. So the difference from v final to v initial is delta v. So I could find the area of the triangle by saying it's 1/2 t times delta v. This isn't terribly satisfying, though, because delta v changes as time changes. So if I add these two together, the equation that we would get for displacement would have two variables, time changes and delta v changes. So we're going to write delta v in terms of time by saying the definition of acceleration is delta v over delta t. If I solve this for delta v, I can say that delta v is equal to acceleration times change in time. I could substitute this in for delta v over here, because acceleration is a constant, and delta t is going to be the same as our time t here. Again, this is a delta t, but the initial time happens to be 0 in my shaded area. So I'm just going to write this as a times t, sub it into here for delta v, and then this term becomes 1/2 t times the quantity a times t. And if I distribute that through, we have 1/2 at squared. So the two terms for the triangle and the rectangle are these. And if we add them together, we get another kinematics equation, that the change in position, the displacement of an object, is equal to 1/2 at squared plus initial velocity times time. And there's a third kinematics equation here, which is the result of taking these two, substituting in for time. You could solve this one for time, substitute it into time here and here, and then simplify it to this third kinematics equation. And I won't show you that here, but it can be done. It takes a few lines of algebra. But these are the three kinematics equations. The last one, as you'll notice, doesn't have time in it because we used a substitution with time with the top two to solve for it. So this one is useful if you happen to have a problem where you don't know anything about the time elapsed during the motion. And these two are useful because this one tells you the position at any time, and this one can tell you velocity at any time. And these equations describe the motion of an object provided two things. It has to move along a straight line. These are equations for one-dimensional motion. And the object has to have a constant acceleration, which means that the acceleration can't be changing. It is not changing. The acceleration could be 0. It could be any number. It could be positive. It could be negative. It just can't change. If the acceleration is 0, by the way, we get the constant velocity kinematics equations. If you make acceleration 0 here, you just get v final equals v initial, which is a constant velocity. If you make acceleration 0 here, you get v final equals v initial, again a statement that velocity is constant. If you make acceleration 0 here, this whole term cancels out, and you get delta x equals velocity times time, which was our kinematics equation if an object happens to have a constant velocity. So we're going to take a look in the next 3 slides at some problems that we can solve using these kinematics equations. The way that I've worked this out, I've written the 3 kinematics equations down here, and I'm just going to do some circling and underlining by dissecting all of this phraseology into physics and then trying to find the equation that will solve the problem for me. These problems are from the book. Number 25 on page 65 from the book says, a speed skater moving across frictionless ice at 8 meters per second hits a 5-meter wide patch of rough ice. She slows steadily, then continues on at 6 meters per second. What is her acceleration on the rough ice? So when the skater reaches this patch of rough ice, starts with some velocity, and then gets slower. So this could be a motion map of the process. This patch of ice, the total length from here to here is 5.0 meters. We know the initial velocity was 8.0 meters per second when she hit the patch of ice. The last velocity upon leaving the patch of ice we'll call v final, and that's 6.0 meters per second. And we need to find the acceleration. So let's circle everything that we know. The 5 meters is a displacement. In fact, if I were to draw a vector to represent that displacement, it would look like this. So it's a positive 5 meters to the right. We'll define right as positive for all of this stuff. So we know the displacement that someone traveled. So I'm going to circle that in these two equations. We know the initial and final velocities. So everywhere there's an initial velocity, I'm going to circle that. And everywhere there's a final velocity, I'm going to circle that as well. And if you take a look at the equations now, there is one that's solvable. It's the third one. It's solvable for acceleration. So I could plug these numbers in and solve for acceleration. V final squared, so 6.0 squared, equals V initial squared, that's 8.0 squared, plus 2a delta x, which is 5.0 meters. And then you could just solve for the acceleration using algebra. Problem number 63 says a toy train is pushed forward and released at x equals 2 meters with a speed of 2 meters per second. It rolls at a steady speed for 2 seconds, and then one wheel begins to stick. The train comes to a stop 6 meters from the point at which it was released. What is the train's acceleration after the wheel begins to stick? So the problem starts with an object moving at a speed of 2 meters per second, and it does so at a constant velocity for about 2 seconds. Then the wheel starts to stick right around here. So the object is going to begin to get slower and eventually come to a stop. We'll say V final is 0 meters per second over here. The train comes to a stop 6 meters from the point at which it was released. So what we actually know is that the total displacement over the course of both motions was 6.0 meters. But this motion over here has no acceleration, and this motion over here has some acceleration, a non-zero acceleration. So we're going to have to study these separately. We can't use one equation to study the whole process because there are two different accelerations. So we'll have to study these two separately. One of the things we do know is that it rolls at a steady speed for 2 seconds. This part of the motion right here, where the acceleration is 0, can be studied using the constant velocity kinematics equation. X final is equal to Vt plus X initial. I could find out how far the object traveled because the things that I happen to know about this equation, I know that the object traveled for 2 seconds with this constant velocity, that this entire motion took 2 seconds. So I know time. I know the velocity the car was traveling, 2 meters per second to the right. So I could find delta x. If I take xi to the other side, this is delta x equals v times t. So delta x is going to end up being 2 meters per second times 2 seconds. So delta x is equal to 4 meters. So this length that the object travels is 4.0 meters. Then technically, I drew this at the wrong spot. Let me ungroup these really quick and just move this arrow over. And over here is where the car begins to stick. And then it accelerates from this point on. So if this is 4 meters that the car traveled, then the rest of the motion over here had to be 2 meters, because we know this whole thing has to add up to 6.0 meters. Right? Ultimately, we want to know the train's acceleration after the wheel began to stick. So we need to find acceleration during this motion. We know the initial velocity, and this is during the accelerated motion. The initial velocity is 2.0 meters per second, because that was the last velocity the car had during this 4 meters of moving. We know the final velocity is 0 meters per second, because it says that the car comes to a stop. Comes to a stop is a way of saying that the velocity is 0. We know the distance that the object is going to travel during the acceleration. It's going to travel 2 meters to the right, so I'm going to say delta x is 2.0 meters. And this should be enough information for us to figure out the acceleration after the wheel began to stick. Because we know delta x, I'm going to circle that everywhere. We know VF and VI, so I'm going to circle VF and VI everywhere I see them. So I could solve for acceleration again using the third kinematics equation. Once I know that acceleration, I could even plug it into here or here to solve for the time it took. This one would be a little bit easier. But they never ask for that. So that's how you would finish up this problem. Going on, I have one more example problem here. It says a rocket car, this is number 67. A rocket car is launched along, typo, a long straight track at t equals 0 seconds. It moves with a constant acceleration of 2 meters per second squared. At 2 seconds, a second car is launched with a constant acceleration, a sub 2, of 8 meters per second squared. And it wants to know at what time does the second car catch up to the first car, and then how far down the track do they meet. So here we have two objects moving, and we want to find out something about the two objects moving relative to one another. So I could write out an equation of motion for both of these cars in terms of this kinematics equation here, one for each object. So I'll say that car 1, it has a position given by 1/2 times its acceleration of 2 meters per second squared times t plus its initial velocity. Well, it says a rocket car is launched along a straight track with this acceleration. At 2 seconds, a second car is launched with a different acceleration. It never mentions anything about the initial velocity. So I'm just going to infer from this that the initial velocity must be 0. So this whole term is 0. Plus the initial position. Again, if this is delta x, this is x final minus x initial equals all this stuff. So I could take initial position, move it to the other side, and have x final equals 1/2 at squared plus vit plus x initial. But the initial position, we get to decide where x0 is. So I think they're both launched at the same place. So we could just make that place 0 as well. So car 1 has an equation of motion that's actually kind of simple, because 1/2 times 2 is equal to 1. So it's just equal to t. The position of car 1 is equal to t, squared, because the squared is here. Car number 2, I could set up its equation of motion the same way, except put in its acceleration of 8 meters per second squared. It also has an initial velocity of 0, an initial position of 0. So the equation of motion for car 2, 8 divided by 2 is 4, would be 4t squared. Now the difference here, it says at 2 seconds, a second car is launched with a constant acceleration. So this car is launched 2 seconds after this car is launched. So the way the times would work out for this, that any time that you have plugged in over here, this one has to be 2 seconds behind. So at time 2 for this one, the time here should read 0. So I'm going to rewrite this as x2 is equal to 4 times the quantity t minus 2 squared. So that way these times sync up. Again, when time is 0 for this car isn't even launched yet. So 2 seconds later, when this car is at a position at 2 seconds, I want this car to be launching. So when I put 2 in here, I'll get time 0 for this car. And this way, I can use these equations to figure out when these cars are going to end up meeting. Because part A asks, what time will the second car catch up to the first? That's when they have the same position at the same time. So what I need to do is say x1 has to equal x2, which is to say that t squared is going to equal 4 quantity t minus 2 squared. I could FOIL this out. This will be t squared is equal to 4 times the quantity t squared minus 4t, because you'll get a minus 2t and a minus 2t, plus 4. If I factor this through, I have t squared equals 4t squared minus 16t plus 16. I have a t squared term here. I could subtract to both sides. If I subtract t squared here and I subtract t squared here, t squared minus t squared gives me 0 equals 3t squared minus 16t plus 16. So this is a quadratic equation. You could either use the quadratic equation solver to get this time. You could use your calculator or some other way to find this. I won't show it to you here, but this is a solvable equation. And once you get the time, there'll be 2 times. One of them will probably be negative, and one of them will probably be positive. It's the positive time that's the meaningful one here. Once you get that time, you could plug it into either one of these equations to find out how far down the track they meet, because it should give you the position of the objects at the time. So once you have the time from here, you could plug it into either one of these to find out where they would meet. So those are a selection of kinematics type problems that you could encounter, this one being rather tricky, involving a system of equations and stuff, but it gives you the sense that you could try to figure out using these equations what's happening with a constant acceleration motion.